In this video, we're going to learn the derivatives of the exponential and logarithmic functions. What makes the exponential and logarithmic functions different from our polynomials is that they have a strict behavior for all values of x. So here I've got a graph of the exponential function e to the x, and the fact of the matter is e to the x is always increasing. That means it's always going up. And compared to all the polynomials, the x to the n type of functions, the e to the x function grows faster than any power of x possible. So it's growing incredibly fast. When you take the derivative of the e to the x function, guess what happens? You get e to the x. That's right. It does absolutely nothing to the function to take the derivative. The derivative of e to the x is just e to the x. So think about that compared to the polynomials that you know. Like for example, the derivative of x squared is 2x. The derivative of x cubed is 3x squared. So each time you take the derivative of a polynomial, the power goes down. That means it's that means that it's increasing at a slower rate. That's not true about the exponential function. The derivative of the exponential is the same exponential function, and so it's always increasing, and not only that, it's always increasing at an increasing rate, right? So if we take a look at the original function compared to the graph of its derivative, we can see that the slope of the tangent line at all points on the function is also increasing exponentially. So e to the x is increasing, its derivative, e to the x, is increasing. Its derivative, e to the x, would be increasing. All of its derivatives all down the line are increasing, and that's kind of tied in with the fact that e to the x is increasing at pretty much the fastest rate possible. Now let's compare that with the natural log function, and if you recall from earlier videos, e to the x and the natural log have something in common. They're inverses of each other. They have a relationship. The fact is that they're inverses of each other. Okay, so what you can think of graphically is that if you drew the line y equals x, the diagonal line right here, if you took e to the x and flipped it over that line, you would get the log function. Likewise, if you drew the line y equals x right here, the diagonal line, and you took this function and flipped it over that, then you would get the e to the x function. Okay, so that's the graphical relationship that speaks to the fact that they're inverses of each other. Now let's think about their rates of change. As we discussed, e to the x is a very, very quickly growing, increasing function. Now what about log x? Does that look like it's increasing? Yeah, well, I've written that it's increasing right here, and you can see that log x is indeed going up higher and higher as the x values increase. However, because it's the flip side of the e to the x function, ln of x is always increasing at a decreasing rate. E to the x is growing faster than all the polynomials. Ln x is growing slower than all the polynomials. That has to do with the fact that it's the inverse of e to the x, so it got flipped over the y equals x line. Okay, so what's the derivative of ln x? I've written it right here. The ddx of ln of x is 1 over x. And if you think about what the function 1 over x looks like, I've plotted it right here, and you can see that as x gets larger, the 1 over x function is getting smaller and smaller. So the rate of change of its derivative is negative. This derivative is always getting smaller and smaller and smaller, so this rate is always decreasing. Okay? That's the difference between these two functions. This one is always increasing, always at an increasing rate. This one is always increasing, but always at a decreasing rate. You see, the larger your x goes on the log function, the log is still going up, but it's just going up slower and slower and slower. And you can see that if I've graphed the slope of its tangent line here, it's getting smaller and smaller with increasing x. Now, the ddx of ln of x is 1 over x, so let me just show you with the two graphs what that really means. You should also recall the x and y intercepts of these two functions. On this function over here, e to the 0 is 1. And likewise on this function over here, ln of 1 is equal to 0. Okay? So the log of the number 1 is 0. That's why it has the x-intercept at 0 right there. But let's say if I imagine the tangent line to the function at x equals 1, if I can see the little line that's just tangent to it there, the slope of that line the slope of that line is going to be 1 over 1, which is equal to 1 right here. So if I plotted its derivative, the derivative would have the value m is equal to 1 right there. Now if I moved over to x is equal to 2, and I considered what is the slope of the tangent line as x equals 2, that's going to be 1 over 2. So you see that's gone down by half. Here's 2 and here's a half right there. And then if I move over some more, x is equal to 3, you can see that the slope of the tangent line is even shallower. And in fact, the slope is 1/3, and there's the number 1/3 on the line right there. So that's why I say that this function is always increasing, but the rate at which it's increasing is always decreasing. This is the slowest function that we can describe behavior with, and this is the fastest function that we can describe behavior with, and that's what makes these two functions different than our standard polynomials. In the next videos, I'll show you how we take the derivative with more complicated compositions of these two functions.